Welcome to our lecture on gestational adaptations. Today, we are going to explore the incredible maternal physiological changes that occur during pregnancy. When a woman becomes pregnant, her body undergoes a series of remarkable, life-sustaining upgrades to support the developing fetus while maintaining her own health. We will dive deep into how the cardiovascular and renal systems remodel themselves to meet these massive new biological demands. By the end of this session, you will have a profound understanding of how biological supply and demand work in perfect harmony. Let us begin by imagining you are trying to water a massive, newly planted garden using the same small hose and water pressure you used for a single potted plant. The water simply would not reach all the new roots, and the plants would starve. In a similar way, when a woman becomes pregnant, she is growing a completely new organ system called the placenta, alongside a rapidly developing human being. Her body must drastically upgrade its internal plumbing system to ensure enough nutrients and oxygen reach the baby without depriving her own organs. This is a beautiful example of biological supply and demand. Now that we understand the overall need, let us look at how the cardiovascular system specifically adapts. Gestational cardiovascular adaptations refer to the systemic hemodynamic changes in the maternal body. These primarily include a massive expansion of maternal blood volume, an increase in resting heart rate, and an increase in stroke volume. Together, these alterations ensure adequate uteroplacental perfusion, which is the continuous blood flow required to sustain the developing fetus. To handle this much higher fluid capacity safely, the body lowers systemic vascular resistance. This means the blood vessels relax and widen, allowing the extra blood to flow smoothly without causing dangerously high blood pressure. Beyond just feeding the baby, these cardiovascular changes serve another vital purpose. Without them, the maternal heart could not pump enough blood to the placenta, which could lead to severe fetal growth restriction or even fetal death. Furthermore, the massive expansion of blood volume acts as a crucial safety buffer for the mother herself. During childbirth, a significant amount of blood is inevitably lost when the placenta detaches from the uterine wall. This pre-established extra volume prevents the mother from going into hypovolemic shock during delivery. It is a brilliant evolutionary mechanism that proactively protects both the mother and the developing baby simultaneously. To truly grasp how much the heart's workload increases, we can look at the fundamental cardiovascular equation. The formula states that CO equals HR times SV. Conceptually, this tells us how much blood the heart is moving over time. CO stands for cardiac output, which is the total volume of blood the heart pumps in 1 minute. HR represents heart rate, the number of heartbeats per minute. SV stands for stroke volume, which is the amount of blood pumped out of the heart with each individual beat. During pregnancy, both heart rate and stroke volume increase significantly. Because cardiac output is the product of these two variables, an increase in both leads to a massive overall increase in total blood flow. Before we move on, let us see this formula in action with a concrete example. We are given a non-pregnant woman with a resting heart rate of 70 beats per minute and a stroke volume of 70 milliliters per beat. By her third trimester, her heart rate is 85 and her stroke volume is 80. We need to find the percentage increase in her cardiac output. First, we calculate the baseline by multiplying 70 by 70, giving us 4,900 milliliters per minute. Next, we calculate the pregnant cardiac output by multiplying 85 by 80, which equals 6,800 milliliters per minute. Finally, we find the difference of 1,900, divide by the original 4,900, and multiply by 100. This shows a massive 38.8% increase, highlighting the immense physiological effort required by the mother's body. Now that we have calculated the increase, let us visualize how these changes unfold over the entire pregnancy. On this graph, the horizontal axis represents the weeks of gestation, and the vertical axis shows the percentage increase. You can see three curves here. The green line shows the heart rate rising steadily. The blue line shows the stroke volume increasing sharply early on and then plateauing. The thick red line represents the total cardiac output. Notice how it rises dramatically, peaking around 24 to 32 weeks at nearly a 40% increase. This visual perfectly captures how the combined rise in stroke volume and heart rate drives the massive increase in cardiac output to support the growing fetus. Just as the heart must pump more blood, the body's filtration system must also upgrade. Think of the kidneys as the body's natural water filtration plant, constantly cleaning toxins and metabolic waste out of the bloodstream. When a woman is pregnant, she is not just cleaning up her own metabolic waste, she is also entirely responsible for filtering out all the waste produced by the growing baby. If the filtration plant kept working at its normal, everyday speed, the extra waste from the baby would quickly build up and become toxic to both of them. Therefore, the mother's kidneys must physically grow and drastically speed up their filtration rate to keep the internal environment clean and safe. To handle this extra waste, the kidneys undergo both physical and functional transformations. Structurally, the kidneys actually increase in length and volume. Additionally, the ureters dilate, which is primarily due to the relaxing effects of the pregnancy hormone progesterone. Functionally, the most significant change is a dramatic increase in the glomerular filtration rate, often abbreviated as GFR. Because maternal blood volume and cardiac output have increased so much, significantly more blood flows through the kidneys every single minute. This massive increase in blood flow physically forces the kidneys to filter fluid at a much higher capacity than normal. This dramatic increase in the glomerular filtration rate is not just a side effect, it is absolutely critical for survival. The heightened filtration rate is necessary for clearing fetal metabolic waste products, such as urea and creatinine, from the maternal circulation. If the GFR did not increase, these waste products would accumulate, leading to a toxic environment that could impair fetal brain development or cause severe maternal illness. Additionally, this hyperfiltration alters how the mother's body handles medications. Because the kidneys are clearing substances out of the blood much faster than usual, doctors must often adjust drug dosages during pregnancy to ensure the medication remains effective. To measure exactly how well the kidneys are adapting, doctors use the standard clearance formula to calculate the glomerular filtration rate. The formula is GFR equals UX times V divided by PX. Let us break down what these symbols mean. UX represents the concentration of a specific waste substance, like creatinine, in the urine. V represents the urine flow rate, which is the volume of urine produced per minute. Multiplying these two gives the total mass of waste excreted per minute. Finally, PX represents the concentration of that same substance in the blood plasma. By dividing the total excreted waste by the plasma concentration, we find exactly how much blood plasma was completely cleared of that waste per minute per year. Let us apply this clearance formula to a real clinical scenario. A physician is evaluating a pregnant woman in her second trimester. Her urine flow rate, V, is 1.5 milliliters per minute. The urine creatinine concentration, UX, is 0.8 milligrams per milliliter, and her plasma creatinine, PX, is 0.008 milligrams per milliliter. We need to calculate her GFR. First, we multiply the urine concentration by the flow rate. 0.8 times 1.5 gives us 1.2 milligrams of creatinine excreted per minute. Next, we divide this by the plasma concentration of 0.008. This yields a final GFR of 150 milliliters per minute. Since the normal non-pregnant maximum is 120, this confirms her kidneys have successfully increased their capacity by roughly 50%. We have covered a lot of ground today, so let us bring it all together. The maternal body undergoes incredible physiological adaptations to support a growing fetus. We saw how the cardiovascular system remodels itself, dramatically increasing cardiac output by raising both heart rate and stroke volume. This not only feeds the baby, but also creates a vital safety buffer against blood loss during delivery. We also learned how the kidneys physically grow and significantly increase their glomerular filtration rate. This hyperfiltration is absolutely essential for clearing the combined metabolic waste of both the mother and the baby. You now have a solid understanding of these vital gestational adaptations.